Hi again. I'm back and talking about failure theories again, right? As you can see. So I'm going to start off with ductile. And if you remember from my last video, I should say, the one that introduced failure theories, right? I talked about the need for ductile versus brittle because ductile materials, as I pointed out in that video, they fail because of shear stresses, okay? We know that from a tensile test because we get a 45-degree failure plane. The tensile test, you're pulling straight up and down. That's a principal stress in the vertical direction, the way I'm pulling my stylus right now. No other stresses. Therefore, if I go 45 degrees from the principal stress state, I get maximum shear. Okay, so what we have then are a couple failure theories that try to take advantage of that. Okay, the first one is something called rather uncreatively, the maximum shear stress theory. Okay, what the maximum shear stress theory says in a nutshell is that a ductile material fails when the maximum shear stress in that being applied to that material, we'll just call it tau max, is equal to that at yield in a uniaxial tensile test. Okay, so what that's saying is if this was my specimen, if my stylus again was my specimen, I do this a lot, right? I pull on it. When I get yield for this case, there's a certain maximum shear stress. The maximum shear stress theory says, well, when you have a maximum shear stress due to any combined loading that matches that shear stress, well, now you're going to have failure of a ductile material. So what does that say about the shear yield strength, right? This actually says something very important about the shear yield strength. Because I can draw a Morse circle, right? And I will. Sigma and tau. And as it turns out, the directions on tau aren't going to matter much. But for the sake of completeness, we'll put them there. We'll put them there correctly. Okay. So let's think about that uniaxial tensile test. I'm going to have sigma 1 here, my maximum, my principal stress, right? Because my uniaxial tensile test, I'm going to use blue just to make it stand out from the text, looks a lot like this, right? With my force and nothing else. So a stress block, if I was to draw one here, I would just have a stress in the vertical direction, right? Doesn't matter what we call that vertical direction. I'm going to call it X just so we have a name, but it doesn't matter. I'm not using it for anything. And since that's the only stress I have, I know it's principal. I don't have any shear stresses. It's a principal stress state, right? That also means my other two principal stresses are really living right here. Remember, we always do have three principal stresses, right? We live in 3 dimensions. So there are always 3 principal stresses. And therefore, those are my principal stresses. Well, Morse circle has to connect them, doesn't it? Right? If I was to draw a Morse circle here, and again, I'm drawing a circle on a tablet screen. I'm not using a compass. Yes, not like I don't own a compass. Yeah, but I'm not using it right now because I value my tablet. And this is one of my lower quality circles, but the point I think gets across. The maximum shear stress is living up here. And of course, same magnitude down here, right? At 90 degrees on Morse circle, 45 degrees on, in reality, I should say, okay? So I'll draw a little green line here, making that a vertical. That, of course, is 90 degrees. So if I have yield of this material in tension, I think you'd all agree that sigma 1 had better be equal to my yield strength. Now, if you haven't seen me do this before, I use capital S's for yield strengths and ultimate strengths and things like that. Why? S for strength, sigma for stress, S is what I look up, sigma is what I calculate, right? Helps me keep things straight in my brain. And plus, this way, I'm not saying sigma y down here, where I have a sigma in the y direction, you know, which one's which. This keeps it straight pretty quickly as far as I'm concerned. So yield, sigma 1 is equal to sy. Well, here is the radius of Moore's circle, right? From the center, there's my center, all the way out to sigma 1, or all the way down to sigma 2 or sigma 3. Well, my maximum shear stress, and this is always true, the first part of this, is always equal to the biggest principal stress minus the smallest over 2, which in this particular case means I've got sigma 1 minus either of sigma 2 or sigma 3. I'll write sigma 3 just because people usually order them 1 bigger than 2, bigger than 3, right? I'm going to go along with that. Well, sigma 3 is 0 in this case. Sigma 1 is sy. I wrote that down. So that tells us that this condition, this maximum shear stress theory, which, by the way, has another name because everything has two names in this field, this is also called the Tresca yield condition. Yes, after the person who came up with it. It's the way we name things a lot of the times, right? Tau max is equal to sy over 2, and we call that also our shear yield strength. So this is the predicted shear yield strength if we're using the maximum shear stress theory. There's a lot of ifs in there. It's kind of a funny thing, okay? So the other thing, though, is there's another way that people decide to look at this, okay? So this is perfectly good. This does a good job. But it turns out it doesn't do a great job. We'll talk more about that in a few minutes, right? It does a good job. So people came up with something a little bit better, okay? Something called the maximum distortion energy theory. And to give another name to this, because of course it has another name, it's also called the von Mises theory. That's M-I-S-E-S once my pen decides to cooperate, right? Again, the person who put it together. What this says, okay, this is based on, go figure, energy, okay? And the failure occurs in this theory, I'll just say failure when the strain energy, more on strain energy in a minute, okay, causing distortion. Hey, I see a distortion in energy in the first sentence. Maybe that's why they called it distortion energy theory, right? Causing distortion reaches that at failure in axial tension or compression. Now, the first thing you have to do is you have to buy how energy, well, you have to buy two things, actually. The first thing you have to buy is that every stress state can really be made into something a little bit more complicated and simpler at the same time. You see, because if I have my x, y, and z axes, right, I can take any stress state. I'm going to make this a general stress state. I'm just going to draw axial stresses. So I'm going to assume this is principal, but it works for principal or non as well, right? And I'm going to have the other three behind. I'll draw this one and this one and this one, right? There's 6 of them, and I've got sigma z and sigma y and sigma x. And I, of course, can have shear stresses. Actually, I said we can draw a principal. I lied, right? I've got shear stresses acting on this thing also, okay? So I've got all kinds of stresses. And I just drew shear on one side. Drawing the rest of it's going to get really ugly. Okay. I can always break this down into two parts. Part one is what we call a hydrostatic component. And if you've seen anything to do with fluid mechanics, this word means something to you. It's a pressure. Notice I put P on all three directions. So I can take this stress state, no matter what it is, and say part of it is if I apply the same pressure to all three directions. And then we're going to add in, I'll put a cube here, but I'm not going to draw any stresses on it. This is something called a deviatoric part. That's everything but the pressure. So I can break any stress state, every stress state, three-dimensional, as complex as you wish. I can make it into a pressure part and an all but pressure part. And that deviatoric part can have axial stresses. It has all of your shear stresses. I'll give it this much right off the top. Here go your shear stresses, right? But there's going to be also some axial stresses. I said I wasn't going to draw stresses on here. I lied, right? I'll call them sigma x1 and sigma y1. I won't draw the ones in the back, though, right? That's the part that causes the distortion. That's the part that makes things change shape. The hydrostatic one just changes the volume, okay? If I take a cube, put it under water under equal pressure from all sides, it's still a cube when I'm done, right? So the hydrostatic part doesn't change shape. It just changes volume. That's all it does. This deviatoric part, that's where the distortion comes from. That's the first thing you got to believe, is I can always do this. And I can show that I can always do this, right? And it makes some mathematical sense. I'm just taking P out of all three directions. So really, this sigma y1 is equal to sigma y minus P. And this sigma x1 is equal to sigma x minus P. So, okay, fine, whatever, right? It's just whatever's left when I take out the same from all three directions. The art, of course, is finding what that value is. And there's math for that I won't get into right now. The second thing you have to buy is energy. And I tell students that, and I'll tell you this too, back in the 20th century, when I was an undergraduate student, one of my least favorite classes was thermodynamics. Didn't like it. Didn't take to it. Didn't like the professor. There was a whole bunch of things against it, right? But I did take a couple things out of it. And one of it is that energy does indeed make the world go round when it comes to this stuff. Even mechanics. Even this kind of stuff here. Because if I draw a simple stress strain curve for a ductile material, I'm going to have a part down here. That's a triangle, right? And if I call this my yield strength, right? Maybe that's what it is. Okay? But as long as I'm in the elastic zone up to that yield strength, right, the area of this is 1/2 base height. 1/2 stress times strain. Now, even if it's not, let me put an equal sign there. Even if it's not the triangle part, the rest of this would just be an integral anyway. So it's in some way the area has to do with stress times strain. Well, let's think about stress times strain is equal to Newton per square meter, right? Times, well, strain is just a unit over a unit, right? It's just a length over a length. That's Newton meters per meter cubed, isn't it? Now, why didn't I just cancel out the meters over meters? Because I wanted Newton meters. Because work's force times distance. Work's a form of energy. Newton's a force. Meter's a distance. That area under the stress strain curve is just energy per unit volume. when I stretch something, I'm going to go into my desk drawer here because I have something that I can demonstrate this with, right? When I stretch something, I put energy into it. I put strain energy into it, right? Strain energy going into this rubber band. How do I know there's strain energy in this, you may ask? I don't know. I can just fire it off like that, can't I? That's strain energy being stored as potential energy. I let go of it, becomes kinetic energy. How else is it going to get velocity, right? So when I stretch something, I do put strain energy into it. So now, knowing that that's energy, stress times strain is energy, that tells us that strain energy has something to do with this distortion. So going back to distortion energy here, if I use capital U, and let's go in 3 dimensions, right? In 3D, my big U, and this big U is strain energy. It's energy that we get from deforming something. And that's going to equal 1/2 of my first principal stress times whatever strain it comes with, second principal stress times whatever strain, third principal stress times whatever strain. I got too much sigmas on the brain, sorry about that, right? And what I can do then is I can then take, using this energy, we can define an equivalent stress that's one number that produces the same energy, right? We often call this the von Mises stress. Sigma Vm is what I typically use for it because, well, I use it for the von Mises theory. And it's going to turn into, for the case of 2 non-zero principal stresses, for the case of plane stress, it'll be sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared all to the 1/2 for the case of plane stress where sigma 3 is 0. Okay, great. So now what that tells us is we're going to have failure then when the von Mises stress is equal to the yield strength. Slightly different condition. So I've got 2 theories for the same material, right? Which one's correct? Really, not really. Okay. What I'm going to do here is I'm going to make a little plane. We'll talk about that. This plane is going to have axes of the 2 in-plane principal stresses. And what we find, first of all, is that the maximum shear stress theory, right? I can draw this kite shape. Okay? And this value up here is the yield strength. Value down here is the yield strength. We got minus SYs on the negative sides too. Anything inside is safe. Anything outside, we presume has failed. And the blue is the maximum shear stress theory, MSS as I call it. Right? Maximum shear stress theory says this. What the distortion energy theory says is a little bit different. I'll draw it in green. Let's call it MDE even. And it passes through a lot of the same points. It has to. Because this point of S with sigma 2 equal to SY, sigma 1 equal to 0, well, that's got to be a failure point no matter what, right? And it makes this ellipse kind of shape. And yes, this time I mean this not to be a circle. Notice it's going through these points up here, right? And notice it's going through, pretty much going through the 6 corners on that kite. And what we find is that experiments, yeah, we have a lot of experiments out here that say, ooh, you know, these X's are failures. These are from experiments, right? And these little circles, well, if I have these stress states, these principal stresses, sigma 1 and sigma 2, it's okay. What we find is that especially down in here, we'll also get some green circles like right on the edge of or just outside. So maximum shear stress theory isn't wrong per se. It's just a little paranoid, right? It's more conservative. The maximum shear stress theory, MSS, is more conservative than distortion energy or von Mises. What does that mean to us? That means that if you have the same stress state, you try the two different theories, the maximum shear stress theory is going to predict a lower factor of safety. It's going to think you're closer to failure than distortion energy does. Which is better? Depends on what you're trying to do, depends on who you're working for, right? And seriously, if I'm making a race car, I'm doing everything with distortion energy, and my factors of safety are probably 1.5 anyway, right? If I'm making a house, maybe I use maximum shear stress theory, and I make the factor of safety 2.5 instead of 1.5, right? It all depends on what I'm doing, what I'm trying to get done. And also what you find is that if you want to go quick and dirty, I mean, sure, I can find the principal stresses and do this math and compare that to yield strength. Okay, great. Or I can do this math, tau max SY over 2. That's a little easier to remember, right? 1/2 the yield strength and tensions, yield strength and shear is a little easier to remember. Distortion energy makes that number a little bit higher, like 15% higher, actually. So which one you use, it all depends on what you're doing, right? I know a lot of finite element solvers, they're going to pull out distortion energy theory for you because they've already computed the energy anyway. That's how finite element methods work, is they work on strain energy. You already have it, so why wouldn't you use it for something, right? So the bottom line is we have these two theories. They run on these equations. The von Mises stress is equal to what's inside those brackets, sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared all to the 1/2. Yes, you can certainly have a case with this. There are versions of this equation that don't use principal stresses. You can look those up, right? To me, I always like to make these things run on principal stresses because principal stresses are fundamental to all this. Here, the maximum shear stress theory, we can use the principal stresses again and take the biggest minus the smallest over 2. And that gets us our maximum shear stress. Or if you want to draw a Mohr circle, well, that works every time too, right? So hopefully this gives you a little introduction to how ductile failure theories work, and we'll get on to brittle next time.